Today we're looking at section 7.1, approximating definite intervals as sums. The basic idea of this section is we're going to want to find the area under a curve, or we're going to want to find an accumulation. If we start with a constant function and we want to find something like distance, that's velocity times time, it's easy to understand that's the area under the constant function between 2 points. Area is just base times height. I can do that without any calculus. Similarly, if I had a linear function, I would take a triangle and find that. The problem is, once my area gets as complicated as a quadratic function, I don't have nice geometric formulas for finding the area under a curve. So what I'm going to do is say, all I understand how to do is find the area of rectangles, and so I'd like to approximate that area by a rectangle. The first way I approximate it is I just put it inside a rectangle. It's got a base of 4, an area of 4. The most that area can be is 16. If I want a better approximation, I slice it into thinner rectangles, and now I've cut it into 4 rectangles, and I look at the heights and add up the area and say the area is actually less than 14. I'd get a better approximation if I did 8 subintervals, and by the time I do 100 subintervals, it's hard to tell the difference between the area under the curve and the area inside my collection of rectangles. This is a method that's pretty straightforward, but is tedious to do. And so in a normal calculus class, we skip over that to something with formulas and then spend a semester learning how to do this with formulas. We're only going to have a day for technique, so instead we're going to look at the numerical methods, and they work well with spreadsheets. So I have my basic function, my area. I'm looking if I have 4 rectangles, the area winds up being 10. In each case, I've found the area of the rectangle by taking the starting point of the subinterval. So that's a very flat rectangle. I started at that point. I then do the rectangle. I'm doing the rectangle on the left-hand side in each case. But what's straightforward to see is if I just went up to a lot of rectangles, it's hard to tell the difference between the area under that green curve and the area in brown, which is the area contained by the rectangles. If you think about computer graphics or television, you have all of these squares and you see anything you want just by making the squares really small and the points close to each other. So this is the basic approach we're going to do, numeric integration. Fortunately, when I try and turn this into something with Excel, there's a basic setup I'm going to use. I'm going to first of all look at it and show functions. I need to have my function, my starting point, my ending point, the number of intervals. The width of an interval is going to be ending point minus starting point divided by the number of intervals. When I look at my points I'm going to evaluate, I'm going to start at the lowest point, $2, and then I simply add the interval at each point. So I simply step in delta x's. My function is x minus 4 times 4 minus x. I evaluate at the first one, drag down, it'll evaluate. The area of a rectangle is base times height. The base is $5. The height is what I've just computed here. Then for my area, I'm going to add up rectangles. Offset we'll get to in a second. I'd like to do this with 10 subintervals. So I quick fill down to 10. I want to make sure to only use the second row in my quick fill here because I don't want to keep going back to the starting point. I'm adding delta x to whatever was before. I continue down. Now when I'm looking at it, what offset says for my area approximation, I'm going to go in the area so far, and since I've got 10 intervals, I want the 10th row down. So I'm going to start in this place, my title, E8, and I want to go down by my number of intervals, B4, and I'm in the right column, so I don't want to go over. So now when I look at this without formulas, it gives me 10.56, which is the approximation I get by the rectangles. Now at this point, I might decide I don't want 10 intervals, I want 100 intervals. And all I need to do is say this basic template ought to go down to 100. Doesn't matter if I go too far because I'm going to that place that was designated, and I get 10.6656. So I got a much better approximation. I could then decide I want 1,000 or 10,000 intervals. I simply have to drag down. Doing this computations are easy, electrons are cheap, so it's pretty easy to do on a spreadsheet. The one thing that's different here is I'm using my offset to say, this is now several pages of Excel stuff. I don't want to have to dig through it, so I'm going to find the answer and bring it back to the top. So this gives me a way of approximating functions. One of the nice things about it is this template works pretty much with any function we're going to consider. So if instead I wanted to do x times 4 minus x times x again, I would need to change my function here, so I know what function I'm using, and I need to change my function here so that I'm using that function. And then I simply need to drag down and quick fill, so I'm using that function for the 100 rows, the 100 for all of my entries, and I get a different area. But again, whatever function I have, I simply fill it in and put that in the function, put that in this general setup, and I can approximate without knowing any formula manipulation. That's the basic idea for today, that we'll get area under a curve, or we'll get accumulation by just taking lots of short intervals, finding how much we add up in that interval, and adding all of those up. And so this is a numeric method that lets us do definite integrals. Thank you.